Yeah, yeah. I will show the title. I'd like this seminar to be very informal, so please ask questions. Yeah. Please ask questions during the. Okay. Yeah. During a presentation. Yep. Today I'd like to show. Yeah. Okay. I'd like to discuss the formation of non-resonant multiple crossing supers. Yeah, which may exist around 40 to 60% of the solar type stars. And I showed our recent result by the n-body simulation and population synthesis calculation. And in particular, I focused on the effect of disk inner edge, like inner cavity or not, or planets, migrating planets stop there or penetrate. And today, I propose some possibility of the planet trap due to eccentricity damping, and not a reversal torque. And in the population synthesis model, we use type of migration, so Tanaka et al. Torque or Paddy-Cooper et al. Torque. Or we also include the resonant trapping and giant impact. So, yeah, maybe many people know that Stefan Woodley present during the conference in Portugal. They say 40 to 6% of solar type stars have a short period supers without any significant sign of gas giant. Is it correct, Doug? Is that
40 to 60% is correct. The other statements about short period and without signs of gas giant, that's not correct.
Okay, so some of them have sign of gas giant.
Yes.
Okay. Yeah. Right. And this fraction is also uncertain. But last year they said 80% of the super system are multiple, and they are not in resonance, non-resonant. So recently they talk about that, and here's Stefan and Michel. So I was thinking between them, and this is my son, so he's also thinking. So question is, why super system is so common, and but our solar system doesn't have any crossing supers. So why? And some of supers, many of supers have masses larger than 10 Earth mass. So why they didn't become a gas giant, accreting this gas? And also, they say location of supers. What's happening? Yeah, location of super system like 0.1 AU. This radius is larger than the radius of hot Jupiters. So why they are located in a little bit outer region? And why non-resonant? Because Tarkam and Paparazzo, 2007, did some simulation, and they showed normally super system locked in resonance, right, John? Yeah. But the observations suggest that they are not in resonance. And why multiple? So many questions arise. So today I address these questions. Yeah.
Which range of mass do you consider super Earth? From how many Earth masses to how?
The definition of super Earth is not so simple. So
Below 50 Earth mass.
Okay.
below 50 Earth, okay.
Until they can detect.
So Neptune is super Earth.
Yes.
Neptune is super Earth, okay.
That's the definition by observers in
Okay.
that 40 to 60.
All right.
Okay.
Okay, so first I showed our result of n-body simulation. This simulation was done by Masahiro Ugihara. He is sitting there, and he made this animation also. Okay, so this is for this is a result of our n-body simulation. This is a snapshot starting here, and this is 3D n-body simulation starting from many small planetesimal, and some bodies undergo runway growth and start to migrate, because we include a type 1 migration here. Then also here we assume disk case like this. So this is a substantive disk case. So here 0.1 AU, we cut off the disk like this, like a tangent hyperbolic function. So, okay, so migrating planet stacked around the 0.05 AU, something like that. This is a close-up. So first one comes and accrete, then here, then the next one comes, and in this case, we assume type 1 migration rate predicted by Tanaka et al. So migration is relatively fast. So first, these guys penetrate all the resonance, then they undergo some cross scattering and sometimes collision. So eventually, always several embryo remain, and they are trapped in resonance. And this system is very stable. And even if we take out the gas, actually, here is this case. So there's almost no gas around here. But even if we take all the gas, they are very stable. This result is consistent with the result by the Targam and Paparazzo. So they always we find several embryo trapped in resonance. But we also did a calculation with slower migration. So migration speed is artificially reduced. So the migration is slow, which means a kind of adiabatic process. So the many embryo trapped in resonance. In this case, this migrating planets penetrate all the mean-motion resonance. Then they stop near the disk cage. Then they undergo cross-scattering and sometimes collision. But this case, migration is slow, so they're trapped in resonance and line up. So many embryo line up. Yes.
So how much slower is this?
I don't remember, but maybe 100 times slower. Yeah. But you see that here's the disk cage, and the outer guys undergo type 1 migration. So outer guys push inner guys. But this system got stuck. So it's a problem. Why these guys push inner one, but they don't go into the inner cavity. I will show you the detailed analysis today. But before going into the detail, let me explain next evolution. So in this case, if we take out this gas, so we take a damping, then they start orbit crossing. So eccentricity gradually pumped up, and eventually they start orbit crossing and merging and collision. It's the same, merging. And finally, we find only several planets. Of course, they undergo cross-scattering and merging. They are not in resonance in the final stage. And the innermost one is located near the disk cage. So the final planets are distributed in a broad range, and it is far beyond the disk lineage. So we can reproduce the non-resonant multiple system at a relatively large orbital radius. So we modeling this process, and we have done some population statistics calculation. I will explain the detail of this calculation, but let me just look through the result. So in this case, I set up the seed planet right here. Then we calculate analytically growth and migration. So initially, mass of the planet, seed planets are low, so they don't move. But as they grow, they start type of migration. Here we assume 10 times slower than the migration speed is 10 times slower than the Tanaka et al. Then this migrate, and here we set up the discrete, so they stop here, and the next one come, and these are resonantly trapped. We mimic we used some analytical model to mimic the result of envoy simulation. After this gets gone, they start orbit crossing. So here, because this is log scale, we can see here. So this kind of calculation, we did some Monte Carlo calculation. This is n-body simulation. So yes, semi-axis and pericenter, apocenter. We also made some analytical model to simulate giant impact stage. Because in this case is stochastic, so we did many calculations, and we average over the result. So eventually we find the super system around 0.1 AU, and the eccentricity is something like this. And this is a case with some particular disk model. Then, yeah, maybe I should comment that. So of course these are non-resonant planet and multiple. And before that, in this case, mass of planet is 0.1 Earth mass, well, at most 1 Earth mass. So they don't start gas accretion. So mass of the planet is too small to start random gas accretion. But after that, they become 10 Earth mass or something like that. But at that time, this gas has already gone. So they didn't start gas accretion. So we get a big rocky planet, but they missed random gas accretion. So this calculation is just for one particular disk mass. So we consider some distribution disk mass, some log normal distribution like this. And then we superpose the result. So here is the result of 1,000 system. Then we find that this is a mass distribution of crossing planet. So there's a clear gap between like 20 Earth mass or 30 Earth mass. And here's a semi-axis distribution. This is a distribution of super Earth. So it's peaked around 0.2 AU. And this is red one is a distribution function for gas giants. So they are located at 0.03 AU or something like that. So they are well separated. But these results rely on the assumption of rigid wall. I assume the migrating planet do not go into the cavity. Here we did some we assume such model, but we have to examine why migrating planet do not go into the cavity. So before that, maybe I need to comment on the disk in the cavity. In the conventional picture, is disk is truncated at co-rotation radius. This is a conventional picture. I'm not sure it is still valid or not. But the conventional picture, here's a protoplanetary disk, and here's a co-rotation radius. So if the spin period is a few days, it is like a 0.04 AU, 0.05 AU, or something like that. Then the disk is truncated here, and after that, this gas accrete along the magnetic field. So if this picture is correct, this location should be like a 0.05 or something like that, co-rotation radius. And if this truncation of disk means magnetic coupling between stellar spin and the disk is strong enough. So which means the spin angular momentum is transferred to the disk through magnetic field. So I mean, planetary stellar spin is slower than the breakup spin. Actually, this is an observation of a spin period of the young stars. This is maybe Orion cloud. So here's some peak around 1 week. This is much slower than the breakup rotation. So maybe this peak corresponds to this picture. But the observation showed another peak, like 1 day or something like that. It is very close to breakup rotation. This is an observation result, but I think there's no clear theoretical explanation. But one possibility is that this case, magnetic coupling is not so strong, so the disk is not truncated. Then the disk extends to the surface of the star. And then the disk just rotates at the Keplerian speed, which means this star rotates like with a rate breakup speed. So one possibility is there's a diversity in disk image, so cavity case and non-cavity case. But it's not clear to me. But here we assume the system is in a cavity. But the next question is, this planet stuck here, or this planet is pushed into the cavity or not? So, yeah. Sorry, disappear. Sorry. My plot disappeared. I don't know. Okay, yeah. So I did some calculation, the simple model, toy model, set up the disk and set up just two planets, and they interact with each other, and also they undergo type of migration and eccentricity damping through the disk planet interaction. The form of so the drag force is very simple. I use very simple one. Ogihara and Ida's paper adopted more detailed formula by Tanaka and Bo 2004. But here I used a simpler model. This is a damping time scale for the eccentricity. So this is a particle velocity and the local Keplerian velocity. And this is a type of migration rate. So these two are parameters. So very simple model. Then I set up here I artificially set up the disk edge at 0.9 AU, and the two bodies start here and they migrate, and the inner one come to the disk edge and then stop. Then outer guy comes. Then here they're locked in resonance. So at that time, eccentricity is excited through the planet-planet interaction. Then after that, some relaxation, and they go into some equilibrium stage. Very steady. Eccentricity doesn't change, and they stop here. You see, outer guy is still undergoing type of migration. And the outer guy pushed inner one, but inner ones stay near the disk edge. This is a result of just n-body simulation, not n-body, two-body, very simple simulation. Also, Martin got the same result. So our code and Martin's code are totally different. So this is not a numerical error. I calculate torque on the body 1 and the body 2. And this is a torque due to the, maybe this one is easier. This is overlap, but this one is type 1 migration torque. So always negative, always inward, push inward. And this is body 2, also this blue one. Torque is also, always negative because it is type 1. And here I neglect reversal torque near the disk edge or something like that to make the problem simple. And this one is a planet-planet interaction. So for inner one, this torque is always negative because the outer guy push inner one and the inner one push outer one. And for outer one, this torque is always positive because the inner one push outer one outside. Then I found the torque, this torque and this torque are balanced. This torque is due to eccentricity damping because the angular momentum is like this. If eccentricity becomes small, angular momentum increases. So this torque is always positive. And this torque and these two torque balance, and this torque and this torque balance. So this is a static state. So this is kind of a schematic diagram. So for body 1, through the eccentricity damping, angular momentum is transferred from disk to the planet, and lose angular momentum through type 1 migration, and also push outer guy. So this one balance with this one, and for particle 2, this torque and this torque balance. So there's steady state. But maybe somebody noticed that the eccentricity of the inner one and the outer one are almost the same. But here, for outer guys, this torque is almost 0. But the inner guy, this torque is very strong. So what's the difference? So difference is clear. Inner one is near the disk edge. So this is a schematic diagram. This is the inner one. Inner one is close to the boundary. When the next one, outer guy comes, the trapping resonance, then the eccentricity is pumped up. So the orbit of the inner one becomes like this, eccentric. But then near the apocenter, this particle go into the disk again. But near the pericenter, no gas. And near the apocenter, usually in the Keplerian speed near the apocenter is slower than the local circular Keplerian velocity. This is just a Keplerian orbit. So always this speed is slower than the local circular Keplerian speed. The disk gas rotates, very close. This speed is very close to the gas speed, so which means that this particle always receive tailwind near the apocenter, but near the pericenter, no force, which means that this body is always kicked from the gas through some drag force. Like eccentricity damping. Then they kicked and kicked, so that this orbit expand. Then the eccentricity decreases, but the semi axis also increases. So the orbit expand. So this force, then I mean, there's some very strong positive torque. Yes.
Are you suggesting, well, I've got a number of questions about this actually.
Yeah,
Are you
yeah, yeah.
suggesting that a single planet
Yeah.
with maintained eccentricity suffers small eccentricity, with a maintained small eccentricity actually undergoes outward migration? That's the first question.
So please repeat again.
Are you suggesting that if you have a single isolated planet
Yeah, yeah.
with a small eccentricity,
Yeah.
that the semi-major axis would increase?
Yeah, right. That's right.
Well, I think actually, I mean, I'll ask the simulators here. I think that actually doesn't happen in simulations. Richard, because I remember a paper by Richard and Winnie where they actually, they actually, well, you actually, Richard. Yeah, first question.
I think the slight difference here is that in those simulations we had a free single planet.
Well, that's why I was asking.
But
I
there's
will
a
come back to
gap.
this.
Right, okay, so in the case of a single planet on an eccentric orbit, we never saw increasing semi-major axis. That's the eccentric.
Yeah, but Martin did.
Even if it goes in and out
That's the whole
of
point.
gas,
Is that
in and out of gas.
Say it again?
Even if it goes in and out of gas this way.
That I don't know, I can't comment on
Right,
that.
right.
I did process like
No, it's not inside. That's the whole point. It's
Yeah,
not
there's
going
cabin.
into the inner hole.
There's a cabin.
I
I can comment that I didn't believe this either when Shigeru mentioned it to me. And so what we're now both doing is implementing Tanaka and Ward just as it stands. In other words, there's a formula at every point in the orbit. You have a local density, a local velocity, an omega, etc. You apply some forces that are provided by the local density and the local velocity, and you continue to integrate the orbit. If you put down a single planet on an eccentric orbit, with modest eccentricity, it will not move outward.
That's why I asked this question.
It will not, under the same simulations that produce this behavior, will not produce an outwardly migrating. A will not increase.
That's the point. Yeah.
But when it's obviously related to the gradient, as Zoe is saying. I mean, if this formula is
This argument
correct,
doesn't depend on the gradient.
no, this
It
behavior
does.
because it's whether you're in the gas at one point and not in the gas at the other. You get it. I think the tests that have been done are in more or less a smooth density gradient.
Hydrodynamic simulations are not in this gap type situation.
Yeah, I've done simulations where it is in a gap.
An outward torque.
It's orbital calculation or fluid dynamical calculation?
Fluid.
Fluid.
I do that.
The question is not outward torque. The question is whether the semi-major axis increases.
Yeah, that,
I think everyone agrees with the positive torque.
Yeah, there's a,
Especially when it goes into E damping or
right.
It's not clear that the positive torque depends
Only in this situation.
Well, that was the other.
Right, okay. I think with the cavity it's clear, you're only applying the torque comparison.
that,
And therefore, if the torque is defined to be positive in Apples,
Yeah,
if
that-
the torque in Apples,
right, so we find that, for type 2.
This is type 1.
Yeah, I understand, but in type 2, but it's kind of type 1, but not completely, right, because it's an it.
Okay, and also a few want to say
Didn't
something.
actually go through the edge.
Yeah.
I think
He's going through part way, I think. Isn't that the sense of the,
Yeah, that's right.
there's a gradient
Right.
at aspect.
Yeah, so the gradient of the inner gap affects the result. So,
I guess my question was whether in this situation it's still okay to take the type 1 torque as being strictly local, because you know the at H offset, which normally doesn't matter, but H here is larger than the eccentricity that's being excited. So
yeah.
you might imagine, therefore, you have to go a little bit more in before you lose the type 1 torque.
Yeah, it is also my question to Bill and other people. Yeah, in the case of type 1 migration torque, yeah.
Sorry,
yeah.
I don't know anything about this, so just forget my, excuse my questions. But I remember this paper by Massé, Morbidelli, and etc. 2006, and they find like cavity acts like a exactly like a planet trapping.
That's different.
That's a
Yeah,
different
that's
kind
a
of
co-rotation.
Why is that different?
That's by the torque being applied at apoceptor, torque which is coming from the material which is undergoing portion orbits. So
It
the
applies
dynamics
circular orbit.
and
Right.
the gas flow are very different in the circular orbits.
Yeah, in the case of type of migration torque, then the torque from the outer disk and the inner disk have the opposite sign, opposite direction, and also corrotation and Lindblad has opposite torque, so they cancel each other. So if there's a gradient of disk, it affects the migration speed and also direction. But my question is, for eccentric damping, there's no, depend in the linear theory, formula doesn't have any dependence on surface density gradient. So only a local value of sigma.
Right.
But my question is it valid for this kind of situation? So
What
surface
did you actually
density.
do for the density gradient? What model did you use for the density gradient?
Oh, this one?
So in the calculations that you're doing, what did you put in for the density gradient?
Yeah, I set up this tangent hyperbolic function.
So what, sorry?
Hyperbolic tangent.
With what width?
Yeah, that's an important point. Yeah, I did simulation with different. This is the width of the tangent hyperbolic function, and I show the result with like this. So this is RH, and this is some smoothing length. Then if I adopt 0.1, then there's some stacking. But if I use, less steep gradient, then these both guys pursue the inner one go to the cavity. Because in this case, typical eccentricity, equilibrium eccentricity is 0.02. So if disk width is, boundary width is 0.01, then this situation occurs. But if we adopt very smooth boundary, then always apocenter and pericenter both in disk, in the gas, and here planet receive headwind. So this kind of expansion doesn't occur. Yeah.
So if this is a super Earth mass.
Yeah.
thing, and-
What one?
This is one response. Yeah. But
Okay.
it doesn't matter.
Okay,
Yeah.
but if it's dipping in and out of this gas,
Mhm.
what is the feedback on the gas?
Yeah, it's also a very good point. Here, I just assume fixed density profile. Yeah.
And would that change the gradient of the edge?
It's
But
a very complicated question because there are MHD flows, the materials coming out of the plane onto the star.
yeah, you mean here planet gain angular momentum. Yeah, planet gain angular momentum, which means that this gas lose angular momentum. So this gas go inward. But there's some, I assume some truncation. So magnetic fields, something like this. So this gas go to the star. So it's not so easy question. Yeah, of course.
But is it true you need delta R over R to be around 0.01?
Yeah.
I didn't quite get that.
Yeah.
For this to work.
Yeah, this is a very delicate value because we consider disk image like a 0.05 AU, 0.04 AU. So that if the width of a disk edge is comparable to the disk scale height, then the 0.01 is is reasonable. But it's not clear it is correct or not. Smoothing length is like scale height.
0.01 is too small, isn't it?
Well, you're right in. If you go right in, you can argue it's very small. But it's still very small, 0.01.
Yeah. That must
Yeah.
be much smaller than H.
No, H use is 0.03, right? What H do you use?
It depends on the location. radius.
At the edge.
Yeah.
What is h at the edge?
Yeah, for example, we consider 0.05 AU, 0.03 AU, or something like that.
And the value of
H
the edge?
over R. What is H over R at the edge?
Yeah, I got 0.02 or something like that.
It's a very idealized model.
Yeah,
It's
right,
sort
right.
of taking the minimum mass and extrapolating
Yeah,
the
yeah.
areas.
It could be much hotter than that.
Yeah,
Yeah.
Right, right. But yeah, I know this value is very marginal. If we take this value, then the such expansion doesn't occur. Also, if we artificially use the slower damping, eccentricity damping, so this is a time scale ratio. I fixed migration time scale, but I changed this damping time scale. Here, damping is very fast, 300 times faster than the migration time scale. But if I use just a 30 times faster one, then again, two bodies go into the cavity because the eccentricity damping is not so efficient, which means that this effect is not so effective. So this kind of trap depends on the parameter, of course. Yes.
I suspect that you would have slow eccentricity damping with respect to the migration rate, not because of a low eccentricity damping, but because of a higher migration rate in that case, because you do not have the inner Lindblad torque, you only have the outer Lindblad torque, because you have only an outer disk. So instead of computing the differential Lindblad torque for the type 1 migration, you should take all the one-sided Lindblad torque from the outer disk, which is of the order of 100 times the differential Lindblad torque, depending on your R.
You mean the
So the migration rate should be much, much larger
And inwards.
and inward.
yeah, but there's a correlation, so
Surely
Okay,
the
you
co-
also get correlation.
Surely the co-rotation torque is enormously strong if you've got a very strong positive system.
yeah.
Okay, okay.
But if it's
That's
on
like
an
a can of
eccentric,
worms.
Well, I think that is likely to be the dominant mechanism by which you stop the planet going into the cavity.
But you've got to ask about whether the structure there, whether it saturates
Oh, well,
or not.
okay.
It's very complicated. But that's another can of worms.
And,
I think it would be stronger than this.
and my question is, Tanaka word formula is okay for this kind of situation?
No.
It is not developed with these conditions at all. I mean, this assumes, that formula assumes that you have two co-orbiting Lindblad waves at co-rotation, and they both damp the eccentricity,
Yeah, yeah.
but they also change the semi-major axis. But if you have both of them, they oppose each other. You probably only have one because they propagate in different directions. So one of them is going to hit this edge and reflect, probably. You're going to lose that one. It's just going to produce a standing wave or something. You really only have one. That one changes the semi-major axis as well as the eccentricity. So you have to put that into the problem.
Yeah.
And trying to remember which one is which, this was quite a while ago. I believe this one would push it in. I think you're leaving out an additional semi-major axis decay that is not in this formula because we have both of these waves. It's just like in the Lindblad in the type 1 migration.
Yeah, yeah.
Like this fellow was saying, if you only have the Lindblad torques on one side, then you get a much faster migration. It's the differential. Well, the same thing is happening here. Both of these co-orbiting Lindblad resonances also change A, but if you have both of them in there because you've got disk on both sides, they oppose each other, and they're not as important then as the zero order ones. So we don't mess with them. We just ignore them because they're not as important as the zero order. But here, that's not the situation. So I actually don't know what happened.
Okay, but is it easy for you to derive formula for this kind? Then if you give me, I use the formula.
What are you doing this weekend, though?
Yeah.
Why wait until tomorrow?
Yeah. So this is a big question, and also I mean back reaction is also a problem. But if as long as this situation we got this kind of some stacking, I mean plant trap due to eccentricity damping. But we need to explore in more detail. Okay, so okay, but we leave this problem in the future, and so let me show some population synthesis model. If you have any further question of discussion, yeah, please please do that. It's okay. Yeah. So we did some planetary synthesis model. So far, in these papers, we neglected interaction between planets. So they grow and migrate independently. Also, the other groups' calculation is the same. But now we included resonant trapping and giant impact because it is very important for the formation of crossing super-Earths. So we have included this process. For the giant impact, yeah, I showed this plot. This is an n-body simulation. This is our Monte Carlo calculation. So it looks very similar, and we compare the result. This is eccentricity and the mass of the final largest body. Yeah, this calculation starts with the many embryos, maybe 15 embryos or something like that. Then start with n-body calculation. So this is a result of by Kokuba et al. This is n-body simulation. So this is mean value, and this is dispersion of 20 runs. In this case, start with the minimum solar mass nebula model. So we use the same, exactly same initial condition for the Monte Carlo simulation. So here is a mean value, dispersion of 20 runs. And this case is less massive case, more massive case. We find a very good agreement between our model and the n-body simulation. So this is a final mass of the final largest bodies, and the eccentricity also semi-axis. We check the second massive one, and also we find a very good agreement.
Shigeru, does that, the 10 times minimum mass, is that affected by type 1 migration? Is the gas
Sorry.
also larger?
Here we neglect any disk planet interaction, just free space.
Okay.
Yeah. So we think that our model is we can use our model. And the good thing is that n-body code is very expensive, calculation expensive. For one particular run, maybe a few days, we need a few days on the PC. But this model is less than 0.1 second with this Macintosh, so very fast. Then, because this is so fast, we can play with this kind of calculation. So I showed again, this is I set up the seed planet and calculate migration, growth and migration. And if the damping time scale becomes longer than the, sorry. A damping time scale of these embryos becomes shorter than the, longer than the instability time scale, crossing time scale, then we allow giant impact. So because we calculate giant impact stage like this, we can also predict orbital eccentricity.
So how do you do the giant impacts?
Uh,
What do you assume?
Yeah, we set up the embryos and we calculate instability timescale. And we choose the shortest pair, and we assume they start orbit crossing. Then the eccentricity pump up. Then maybe neighbor embryos are also eccentricity excited. We estimate the eccentricity, like surface escape velocity, and we use some random number. Then we assume some orbit crossing among the several orbits. Then again, we randomly choose two pairs and collide with each other, yeah, something like that.
Actually, the sigma, the width of the Gaussian, well, it's Rayleigh's distribution. Okay. The width of the Rayleigh's distribution is related to the surface escape velocity of these super Earths to the local Kepler velocity. So these are described in some.
But you assume that they simply grow.
But you can work out the growth times. That's also well known.
No, I mean you lose no mass. You lose no mass in these giant collisions.
Oh, yeah, right. It's merged.
Right.
Yeah, and the eccentricity growth timescale I use formula by derived by Jirin. So yeah, so we find a final distribution eccentricity and mass, and also this calculation is a little bit complicated, but still for this kind of run, a few seconds with this Macintosh, so I can play with this kind of calculation. And yeah, so you find that in the outer region there's no giant impact. This is because we calculate the surface density of planetesimal. So this is the evolution of surface density of planetesimal. You find that in the inner region, like inside 1 AU, all the planetesimal are accreted, so nothing there. But in the outer region, so even after the 100 million years, planetesimals are huge. So the dynamic friction is very strong enough. So dynamic friction is strong enough to prevent orbit crossing. So I always check the mass of the embryos and the total mass of the planetesimal. If the total mass of the planetesimal is larger than the mass of embryo, I stop the, I don't allow the giant impact. So in the outer region, there's no giant impact. So we find that this is very common result in the outer region because accretion is very slow. Even after 100 million years, there are a lot of planetesimals, but unless gas giants are formed. If gas giants are formed around here, planetesimals are ejected and these are decreased. So we find that some implication in the inner region as giant impact occurs. So there some maybe stochastic production of dust grains, but in the outer region there's so many planetesimals. So continuously, dust grain produced unless gas giants are formed. So my prediction is that maybe the existence of debris disk is anti-correlated with Jupiter, and also we don't have any threshold. If we consider formation of gas giants, we need 10 Earth mass core, so there's some threshold. But here we don't need, we don't have any threshold to make debris. So maybe metallicity dependence is very weak. So, but I didn't do any detailed calculation, just a comment. Also, we can do calculation with no cavity. Of course, everybody go inside. Then planet in the inner region just disappear. Also, we can do a calculation like this. So here I adopt Pade-Cooper's talk, and this talk is applied to the optical thick region. So this is some kind of artificial treatment, but here initially I assumed boundary optical thick disk and the thin region at 10 AU. Then I artificially change the location with like this one, yeah, exponential decay with the disk depletion time scale. When the disk gas becomes, surface density of the disk becomes small, then the optical thin region may expand. This is just an artificial treatment. So this region is Pade-Cooper's region. This is Tanaka's region. Then, of course, in this region, planets migrate outward until these planets go to this boundary. But this boundary migrate inward, so that everybody go inward. Yeah, this is same as the same as the discussion part in the Pade-Cooper et al.'s paper. Yeah, they discuss same thing. And but we find that these bodies first migrate outward and inward, so the region around 1 AU just swept up. So no planets remain in this particular calculation. But I didn't do any systematic calculation. I just did some test calculation like this. Okay, so maybe I run out of time. Yeah. Just a few slides. This is just one particular run, but because the calculation is so fast, I can do many calculations. And giant impact process is a stochastic process. So with the same condition, I can do simulation with different random number. So for this case, here I did 20 runs with the same disk condition, but different random numbers. Then I calculate the mean value and dispersion, 1 sigma dispersion. This case is a little bit noisy, so maybe this is okay. This case, I assume the cavity and Tanaka's formula, and but with some reduction factor. So C1 equals 0.3 means 3 times slower than the Tanaka's formula, but the function is the same. Just the numerical value is different. So this one starts with a less massive disk, minimal solar mass disk, and massive disk. But this is just a little bit noisy. So I take out these two. So relatively slow migration case, relatively fast migration case. But you find that in both cases, we find that super Earth near 0.1 AU, independent of migration speed. This is reasonable because the bodies migrate inward, then stuck near the disk inner edge, then collide with each other after disk gas depletion. So the result doesn't depend on the migration speed. Also, there are always several, and they are not in resonance. And before the disk gas, before they start orbit crossing, their mass is small, so they don't start any gas accretion. So after the disk gas depletion, they become big enough. But at that time, disk gas already gone, so they don't accrete to gas. So we don't find any gas giant here, just a big rocky bodies. So this result is could be consistent with observation, and also maybe I cut here. We did this is superposition of 1,000 system with different disk mass. Then we find this kind of peaks, and also we calculated like this. We find that in this set of simulation, we find 30% of the system have the super Earth in this region, but it is still smaller than the observational rate. But we find a significant value. So this fraction is much larger than the stars with gas giant, because we don't need any big core. We just collect the small guys, and after this has gone, they start orbit crossing to form the big one. But again, I point out that this result rely on the assumption of rigid wall in a boundary. So everybody got stuck near the boundary. It's a big assumption. Okay, so let me summarize. Both we did n-body simulation and the synthetic planet formation model to produce the non-resonant multiple short period super system, and the orbit and distribution of orbit and mass and frequency could be consistent with observation. But also we found the formation of closing planet depends on the depends sensitively on the condition in a boundary of the disk, which is not so clear. But if so cavity case, non-cavity case, or planet stuck there or penetrate, it produces a diversity. So for example, our solar system doesn't have any closing supers. So, but many stars have closing supers. So such diversity may be produced by in this condition. So we need to explore in more detail, like a cavity or non-cavity, and how magnetosphere evolve, or what is the exact condition for the such stacking, it is real or not. So we need to explore these in the disk problems. Okay, I stop here. Thank you.
So thank you very much for this stimulating seminar. Are there any further?
Am I right in thinking that you don't get any depletion of planetesimals if you don't form a Jupiter? That if so, that's a problem, right? No debris disks, because that was between 1 and 10 AU. There was lots of planetesimals that weren't depleted, but up to 100 million years, but you don't see debris disks.
I think it's okay. The point is that you certainly can form the core of Uranus and Neptune. There's no gas giant. It has initiated the onset of gas accretion. Nevertheless, the surface escape velocity already exceeds the local capillary speed. So the very attempt to try to build up that kind of core, you can some scattering further, but probably not really rich. I think what it's referred to here is there may be a correlation between systems where if you see a gas giant and if you see debris disk at the same time, then the debris disk tends to associate with those gas giants with relatively long period, but not associate with gas giants that is close in.
Yeah, my statement is not so detailed, just a small comment. Yeah, in our solar system, there's Jupiter and Saturn, and also we have Kuiper belt, so it produces debris. So,
well, I was thinking about the debris that's between 1 and 10 AU.
1 and 10 AU.
Not the debris disk that's further out on the Kuiper belt. That could be related, could be unrelated.
You just mean that just
below 10% of all solar type stars have debris disks detected at ages like 100 megayears. Is that correct? What you're asking?
Yes, I think
So
it's
it seems to be
smaller
a
than that,
kind
that
of a
have debris
contradiction,
that's
right?
less than 10 AU.
Yes.
So the ones
Yeah.
that do have debris less than 100 million years, it's further out. You're looking at Kuiper belts, you're not looking at the regions between 1 and 10 AU. They're generally empty.
Okay. So it's the emission short part of 24 microns is extremely rare. So it's a few percent.
Yeah,
On
It
what
is-
time
it is
scale? On system older than what? Yeah.
10 million years.
Yes.
Okay.
So you're saying you don't get rid of the mass. So as long as you can keep the mass, you're saying you keep the mass, but as long as you don't turn the mass into dust.
Yeah.
Mass is at a lower level because it didn't get a big core, right? So first of all, it's already at a lower level. Otherwise, you would have had a gas giant.
Yeah, what do you mean by lower level?
What is
It's
lower
to-
level?
You didn't build up a core. It's
Oh, you mean that okay, right, that it's lower mass.
yeah,
Each
you didn't
object is lower.
initiate the process of forming a gas giant.
No, but
But you
you'd
don't need
still
very
have
much mass to
collisions.
see,
You don't need, you don't
see
need,
dust.
yeah, you still have
Right,
collisions.
right,
between
right. But the
clusters.
point is that if you put it mostly in the big ones, and you clear out the small ones. Okay, I mean, if you have some clearing mechanism that get rid of all of the sort of rock down to a 10-kilometer in size. At some point, I mean, some size. Okay.
Wait,
Get
so-
rid of that, then you're okay.
Wait, but what you're saying is that, so we just have, more medium-sized bodies.
So small.
No.
And, no, seriously. No,
No,
really,
but
I do have a
that
serious
is
question.
Morbi-sized body is to explain. I would never agree with Morbi. It's actually it's to explain type. It's to explain Astrogal's size distribution. It's not to address this
No.
particular issue.
I
Right?
know. But what I'm saying is that it doesn't really matter what size the objects are. You're still going to have little collisions, and those collisions are still
If
going
they're
to
big
degrade.
objects,
Yeah.
if they're relatively big objects, you
Yeah.
can put in several Earth's mass. It's not a problem.
But you
They
would
just
see
don't
it. Why
collide.
wouldn't you see it? You would
That's
have
because
collisions.
there's a cutoff in this size distribution that's small n. So the collision timescale is long.
Okay.
Yeah.
So you're saying that all the mass is hidden in a few medium-sized objects, not too big, not too small.
During the gas depletion, during the depletion stage, there are many dynamical influences that can cause preferential clearing of some particle size.
Okay.
Possibly.
Okay.
Okay. And
Okay.
you can get rid of the brakes without getting rid of the building. That maybe that would
You need to get rid of everything, apart from the big things, and then they have to
right, but
not
that's-
collide.
But everything is down to some size, right? And what is that size? But that is an interesting question, right? And it's not that difficult to estimate.
This could be more like the terrestrial planet region further out than really thinking far out, where clearly, large radio, clearly everything is still going on at 10 and 100 million years. But here, fewer years, don't form. It would be crazy to say that you could have everything gone up to some size, not colliding very much.
No, but you can, during the gas depletion stage, you can influence all of the small stuff. It's not that they didn't get produced. They just cleaned up somehow through, either sweeping secular resonance or whatever process you can get rid of, because the dynamic load, the drag on the small guys is different from on the large guys. You perturb them somewhat. There could be some influence. And that's probably that's one of the things that Matiko is trying to look into. This is what we call the size distribution for solution for Morbi's problem.
Yeah.
It's not clear, but it's just a possible.
sweeping secular resonance would only work in certain configurations. of
Sure,
giant
sure,
plans.
sure, of course.
So
Of
you can't
course.
evoke that for everything.
Of course, yeah. But who is to know that if you have several, instead of one big Jupiter, but several modest, several Earth-sized object with modest eccentricity, okay, then it would be very different. You know, each one, the secular resonance is much weaker, but you have several of them that cover more area, and you can do something. Maybe. It's not clear.
So the program for next week is still under construction. And, I'm not sure your emails. Probably includes some sort of social event, probably on Wednesday. But that also is under construction. Anyway, let's thank Shigeru.
Okay, thank you.